This video is confidence intervals for estimating a mean when the population standard deviation is known. Okay, so we're looking at example 8. Component lifetimes, changing confidence levels. So, in a simple random sample of 100 electronic components produced by a certain method, the mean lifetime was 125. Assume that the component lifetimes are normally distributed with a population standard deviation of 20. Construct a 90, a 95, and a 98% confidence interval. So we're going to do all three. So remember, here's the formula. It is x bar plus or minus the critical value times the standard deviation over the square root of n. And for all of these, x bar is 125. That's the sample mean lifetime. And then the z, the critical value, that's going to change. Your standard deviation will be 20. Now notice they use the notation for population standard deviation. They also use the word population standard deviation, so we know it's a population standard deviation. It says it's normally distributed, and the sample size is big enough, so we're good there. So n equals 100. Now all of that is the same. What's going to change is your critical value based on your confidence level. So let's do the critical value for 90. Oops. The critical value for 95. And the critical value for 98. So if, looking at the first one, if the center is 90% for the confidence level, that leaves 10% on either side, so 5% on either side. So 90% in the middle, 10% between the two sides, which means each individual side is 5%. So our z in this case is equal to INV norm, and we're going to put in 0.0501, and let's see what we get. It looks like we got 1.645 negative, but remember we dropped the negative. Alright, let's do the next one. The next one, if 95 is in the middle, that leaves 5% left over, and then among two sides that'd be 2.5% or 0.025. So we're going to do, for this critical value, INV norm 0.025, 0, 1. So let's see how that changes things up. It looks like we get negative 1.960, and again we drop the negative. And then for the final one, if 98 is in the middle, 98%, that leaves 2% left over, so each side is 1%, or 0.01. So our critical value is INV norm 0.0101. And let's see how that changes the critical value. That makes the critical value negative 2.326, which we drop the negative again. Alright. So now let's go to the side here to find the confidence intervals. For the first one, we're going to do x bar plus or minus the critical value. So this one is for 90%. 125 plus or minus the critical value, which was 1.645 times 20 over the square root of 100. And you're just going to type that in the calculator. And we get 121.71 as the lower boundary and 128.29 as the upper boundary. So we're 90% confident that the true mean lifetime for electronic components is between 121.71 and 128.29. So next, let's do the 95th% confidence level. So we're going to do the confidence interval for that. So almost the same thing, 125 plus or minus, but instead of 1.645, we replace it with 1.960 times 20 over the square root of 100. And we get 121.08 to 128.92, so we're 95% confident that the true mean lifetime of electronic components is between 121.08 hours and 128.92 hours. And last, let's do our 98 confidence level, or 98%. So that gives us, so for 98%, that gives us 125 plus or minus 2.326 times 20 over the square root of 100. And we get 120.348 to 129.652. So what's going on here? What happens as the confidence level increases? So let's look at the first one. When it was only 90%, it went from 121.71 to 128.29. If you look at 95%, it goes, the lower boundary goes even further down. It's farther to the left of this one, 121.08 to 128.92. This one is farther to the right of this one. So what has happened here is the confidence level or confidence interval has gotten wider. So whereas the 90% one may have been this long, the 95% one is a little bit longer. And if you look at the 98% one, that one's even wider. It goes all the way down to 120.348 and all the way up to 129.652. So that one is even longer. So as the confidence level increases, the confidence interval gets wider. The portion that's changing is this part right here. If you look at the top of the screen, that's the margin of error. So as the confidence level increases, the margin of error increases, which also increases the width of the confidence interval. So speaking of margin of error, this is kind of illustrating what we just saw. If we have a smaller confidence level, that means the margin of error is smaller, but the confidence interval accurately estimates the mean only, it should say 75% of the time. But you can see you have a very narrow confidence level. They're pretty short. But if you look out here, you have all these like this right here. So what's going on is the true mean is right here in the center. There's the true mean. So if the line crosses the mean, that's the confidence interval crossing the mean. That means it has correctly estimated that the mean is within those boundaries. But you can see there's so many where that's not the case. So 75% of the time you will correctly guess it, but that means 25% of the time you will be in error. If we increase our confidence level, our confidence interval will get wider along with our margin of error getting larger, and it's a little bit more accurate. So it's correct 95% of the time. But if you look at the difference between the two, the confidence interval here is much more narrow. It's narrowed it down quite a bit more, but it's only right 75% of the time. This one, it's a bit wider, so we've not narrowed it down as much, but we are more accurate. And then the 99.7% confidence level, the margin of error is pretty large. So look how wide these confidence intervals are. But you can also see almost every single one of these lines go through the true mean, which means it's accurate almost every time. So what is the correct choice here? We could say 99.7 would be the best way to go because you're almost always right. But you haven't really narrowed it down to a very small interval. That's still pretty wide. So I think 95% out of these three is definitely the better. Because while this one is not as narrow as the 75%, it's more accurate. And it is accurate 95% of the time, which is not bad. And the reason it's better than this last one over here is because the confidence intervals are much more narrow, and we're narrowing down what the true mean is. That's a smaller range, which would be a better guesstimate as to what the true mean is. Now let's talk about calculating sample size. This is the formula you're going to use if you want to calculate the sample size needed to find a confidence interval to estimate the mean when the standard deviation is known. So look at the pieces here. N equals the critical value times the population standard deviation divided by the margin of error. M stands for the margin of error. M equals margin of error. And then we're going to square it. And then if you can look down here at the bottom, it says whatever you get, you're going to round to the next integer. So if you get 81.1, you're going to round it up to 82. If you get 81.5, you're going to round it up to 82. So no matter what, you're going to bump it up to the next integer. So let's try this one. The population standard deviation for the age of students at college is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of these students, how many randomly selected students must be surveyed? So remember, N equals the critical value times population standard deviation over the margin of error squared. So let's look. We got to find this. So let's go to the top. If the center is 95, we have 0.025 on either side. If we do I and V norm, 0.025, we get 1.960 negative, but again we drop the negative sign. So that's our Z. Our sigma is 15. That's the population standard deviation. Our margin of error, that's how accurate we want to be. We want to be accurate within 2 years, so the margin of error is 2. So now we're just going to fill in the blanks. So N equals 1.960 times 15 over 2 squared. So make sure you do everything inside here first. 1.960 times 15, then divide that by 2, and then whatever you get, make sure you square that. That's different than a square root. We're squaring. So make sure you use the squared key. Anyway, we've got our correct answer, but remember we need to round it up to the next whole number, which would be 217. And that hopefully makes sense because this is a sample size. You can't sample 216.09 people. So if we only sampled 216, that's not enough because you need that extra 0.09. So to make sure you have enough, you bump it up to the next number, which would be 217 people would be what we would need. Okay, so we're almost at the 15-minute mark again, so I'm going to stop this video and we're going to pick up with part 5.